Okay, so as I said, we're starting antiderivatives. Anti meaning the opposite of taking the derivative. This is also called integration. So these are similar to what we talked about in the warm-ups. It says the derivative f of x of a function, capital F of x, is given. Can you figure out what capital F of x is? So right here they're saying this is the derivative. The derivative of some function is 0. What was the original function? Anyone know? It'd be any constant, wouldn't it? It could be 5, it could be 10, it could be 1,000,000. Any constant would work here. All right, what about this one? This is our derivative. What would the original function have been for us to get that derivative? Michael, do you know? 4x? Just 4x? Is that the only one? Yeah, because it could be any constant, couldn't it? Good. All right, getting a little bit more challenging. What about if we want to get 2x as the derivative? What would the original? Natalie? Just x squared? Plus any constant, right? Good job. And then what about to get 3x squared? What would the original have been for us to get 3x squared? Lizzie? X cubed, right. Let me write this one as an integral, though, just to show you. What we're really doing is the integral of 3x squared dx, and that answer that you just gave me, that x cubed, that would be the answer to this. So when I'm asking you to find this f of x, capital F of x, finding that antiderivative, this is another way it can be written. The integral of that function with respect to x, that means that's our variable, would have been x cubed plus c. So in the warm-ups, we talked about that pattern. And given that f of x is the derivative of capital F of x, and that derivative is kx to the n, okay, what did we say we do to the n, everyone? Add 1, right? And then what do we have to do to whatever that coefficient is? We had to divide it by that exponent, which that exponent was n plus 1. Good. And then what do we have to put after it? Plus c. Excellent. So that would be our formula. So coming down here, it says the antiderivative, f of x, with respect to x, is given this notation right here. This is the integration symbol that I keep referring to. So integration, finding the antiderivative, is the inverse of differentiation. So those are inverse functions. So we have a bunch of basic integration rules that are listed on page 244. They're also on your green sheet. They're also on the inside cover of your book. But the most important ones I wanted us to write here. So what do you think on this? The integral of 0. Constant, right? Has to just be a constant. So what if we're given a constant? What would be the integral of a constant? Look at what we did on the board for number 1. Good job. Kx plus c. This one we already talked about. This one is, the only difference here is this one has a coefficient of 1. This one has a coefficient of any other number. So this would be kx to the n plus 1 divided by n plus 1 plus c. And this is the one we're going to be using over and over again. So the faster you can get the hang of that, the better. All right, what about the integral of sine x? We want to think, what is it that would have a derivative that's sine? Anybody know? What do you think? Say it again? Close. Well, you wouldn't have to have the 1. You're right, it could actually just be negative cosine x. I mean, the 1 makes it kind of easier to understand, but it could be any constant, couldn't it? So we could say, oops, c, not k. So negative cosine x plus c, that would be our integral. But he's right, 1 minus cosine x would also have that derivative, but that would just mean that our c is 1, okay? Then what would have a derivative of cosine? How do we get cosine? If we take the derivative of sine, right? So this is sine x plus c. And all of these are on your green sheet. If you look at the back of your green sheet, all of these integral formulas are listed there. We've only worked on the front so far, but the back also has these integrals because we've only done differentiation up to this point. All right, so we're going to integrate each of the following. So on this first one, I have to identify what n is. N is 1 in this case. So to my exponent, I have to add 1. And then whatever my coefficient was, I have to divide by that new exponent. So again, my exponent was 1. I had to add 1 to it, I got 2, and then I took my k value and I divided by that new exponent. And so then I'm going to have 2x squared plus c. And then I just want to do a little check. I'm going to take the derivative of this to check. 2 times 2 is 4x, derivative of a constant 0, so it checks out. All right, let's do the next one. We write down the 2, we write down the x, but what do we do to the exponent? We have to add 1, right? And so Avery, what's going to go on the denominator? And then what do I have to put it back here, Peter, after it? And then we just simplify it. So it's 1/2 x to the 4th plus c. I just always check it real quick. 1/2 times 4 is 2x, subtract 1. Yes, that is correct. Now, in order to use our formulas, it has to be in this form, x to the n. This is not in x to the n form. So I have to rewrite this one in x to the n form. So what's another name for 1 over x cubed? X to the -3, right? And now that we've done that, all we have to do is add 1 and divide by that value. So I'm going to take my -3, I'm going to add 1 to it, and I get -2, and now I have to divide that coefficient by -2. Now, most math textbooks, you look in the back, they won't have that answer, because to have things simplified, we do not want to have any negative exponents. So I could write this as 1 over, and I'm going to put the negative right there, 2x squared plus c. I can put that negative anywhere. I can put it here, top, bottom. It all means the same. Let's go to the back. Okay, so looking at example 4, we have to have this in the correct form. We have to have kx to the n. So how are we going to rewrite this then? Anyone know how I can rewrite that? Good, Peter. So it's 2x to the -2 dx. That's just another name for the original problem. I write my coefficient, I add 1, what's my exponent going to be? If I add 1, -1, and I have to divide by that, and then I have to say plus c. So simplifying this, this would be -2 over x plus c. That's a better way of writing it. No negative exponents. How would I rewrite the other one so that it's in that x to the n form? X to the 1/2, right. So I have to think of this as x to the 1/2. Here's my n value. My exponent's always the n. So I write my x. I don't have a coefficient. I have to add 1. If I add 1, I get 1/2. What's that as a fraction? 3/2. Now I have to divide by that 3/2. But dividing by 3/2 is the same thing as multiplying by 2/3 plus c. The back of the book may have this answer, but it may have this also. Would you understand that those two are equivalent? Maybe not. Let's talk about why. X to the 3/2, what does that mean? Well, it means the square root of x to the 3rd, which is the square root of x times x times x. As soon as I have a pair of x's, one comes out, one stays in. Does that make sense why those are equivalent? It should. So if you check the back and it has something different, just make sure that you understand why it's equivalent to what you have. Generally speaking, if this is a radical, we write this as a radical, unless it's very complicated to do, which is what's going to happen down here. But first, let's look at number 6. If we have a coefficient in front of sine or cosine, you can always pull that out in front. As long as it's a constant, you can pull it out in front and just not have to deal with it. And you just carry it down as you go. And that's a nice rule to have. We can do that with any coefficient that's a constant. If it's an x, we couldn't do it, but if it's a constant, we can. So the integral of sine is going to be negative cosine. Okay. Number 7, this one's pretty challenging. You have to divide each one of these by radical x. So we're going to have the integral of x to the 3rd over x to the 1/2 plus 2x over x to the 1/2 minus 1 over x to the 1/2. Every one of those is getting divided by x to the 1/2. What is the rule if we're dividing and our bases are alike? What do we do with the exponents? Subtract them, right? So what do I get if I have an x and I do 3 minus 1/2, that's 2.5. So what's 2.5 as a fraction? 2.5 as a fraction is 5/2. So that's my new exponent there. Here I have a 2. I have 1 minus 1/2. That's just a half. How would I rewrite this one so I can have it in the numerator? X to the what, Casey? Negative 1/2. All right, so now think about what your rule is. What do we do to these exponents? We have to add 1. So if I add 1 to this, I get 5/2 plus 2/2. That's going to be 7/2. 2/2 is just 1. That's what I wanted to add on. Now, am I going to put 7/2 or am I going to put 2 7s? 2 7s, because I multiply by the reciprocal. Here again, I'm going to add 1. That's 2/2. That's 1. So that's 3/2. Then I'm going to have to multiply by the reciprocal, because I don't want to have a complex fraction. So that's going to give me 4/3. Again, add 1. Negative 1/2 plus 1 is 1/2. What's going to be the coefficient here? I need more people. I've only seen a couple people show me. What's going to be the coefficient? 2. We multiply by the reciprocal. And we're just going to leave this just like that. Things that are real complicated like that, to write that in radical form would be quite a feat. Eventually, I might make you do that just to practice some algebra, but for now, this would be sufficient. Okay, the next one. This has 2 reasons for being here. One reason is that you can see that we can also take integrals with respect to y. The other reason is this is a product. I just said earlier we cannot do quotients. We had to get rid of that quotient by dividing each term by that denominator. We also can't have products. So we're going to have to multiply this through to get rid of the product. So what's y times y to the 2/3? When our bases are alike, I'm trying to multiply these. Bases alike, what do we do to the exponents? Adponents, as I'm telling you the answer, is add them, right? So what's that going to be then? Y to the 5/3, right? Plus, and then distributing this, it's just y to the 2/3. And now it's very similar to what we did before. But now if I'm going to add 1 to this, what am I going to have to call 1? Common denominator, so call it 3/3, right? That's the name for 1 I need. So when I add 3/3 to that, I'm going to get y to the 8/3 multiplied by the reciprocal. Add 1 to this. What do we get, guys, if we add 1? Quickly. Thank you. And then multiply by the reciprocal plus c. And we'll just leave it just like that. Okay? Any questions there? So you guys have problems to do in your book. Now I want to show you something with your book. Your book tries to make the problems seem easier, but I've always found that in the process they make them actually harder. So when you start with number 9, it's going to have this table method. It's going to say rewrite, integrate, simplify. You do not have to do it that way. You really do have to rewrite to be able to do the problem. But, you don't have to fill in the boxes. Everybody's like, do I have to copy those boxes? No, just do the problem. Okay? So 9 through 33, every other odd.